So in this video, we've combined a few things. We're going to start out talking about the delta function and spend most of our time on that, but we will touch on periodic functions afterwards and then do a recap of all the different approaches we've learned for Laplace transforms, and hopefully we can kind of contextualize them better now that we've seen all the properties that we're going to cover in class. But starting off with delta functions, we're going to begin defining the delta function and how we take Laplace transforms of it. And I will end up drawing a little picture of it for you. So we're talking about the Dirac delta function. Which is given by this function. It's the delta symbol, the little one, not the big one. And it's specified at some argument t minus t0. And all the function does is it takes on value infinity when t is equal to t0 and 0 for all other t. And so if we wanted to sketch this at t0, it's going to be like infinite value, and then it's 0 everywhere else. And so as it approaches t0, it kind of like steeply is going to have to jump up to hit that infinite value. And then the other thing that is useful to know about the delta function is that the integral of the delta function evaluated for all time is 1. The reason we learn about this function is because it acts like a pulse at t0, so it's telling us like if something suddenly happens and we wanted to describe that in a differential equation, we could do it with the delta function. And then if you want like mathematical intuition for how the delta function is behaving, you can think about it like a piecewise constant function. That's like 0 all the time. Maybe I'll do like a little wavy line. 0 all the time. I won't because it counts as scribbling. And then takes on some value close to t0. But it just happens over increasingly narrow intervals around t0. So instead of that first picture I drew, as your interval gets more narrow, it's going to be like that. And then it just gets more and more squished. And then that little tiny non-zero piecewise part takes on higher and higher values over smaller and smaller regions around t0. The delta function behaves nicely for working with it in a differential equation. It's linear. So you can take sums and scalar multiples of it the same way you can of Laplace transformed variables. And it has a Laplace transform. L of delta t minus t0 is going to be e to the minus s times t0. And so, for example, if we wanted to compute L of 4 delta of t minus 2 pi, we would do it like this. So by linearity, we can go ahead and pull that 4 out. And then I just have to identify what my t0 is. And in this case, it's that 2 pi, the thing I subtract from t. And so then I can just plug into the formula e to minus s times 2 pi for my t0. or 4e to minus 2 pi s, because usually we like to have numbers before variables. So that is the delta function. I know this was a pretty short intro to it, but the initial value problem gets a little bit long, so I'm going to go ahead and pause here and move over to the next video.